All right, so now we're going to talk about how simplicial maps induce sort of maps on homology. Okay, so this is the concept of induced maps. So, so one observation is the following: that continuous maps from one topological space to another maps cycles to cycles and it maps boundaries to boundaries. So you might think that this would imply that the homology groups are invariant. It's like under these continuous maps, and that's not quite true because so these well, in any case, it's like, so the point is that they do induce maps between sort of homology groups. So they therefore induce maps between homology groups. But they're not necessarily the same groups, okay? But they're not necessarily the same. And the reason basically is because so cycles of the original space can end up becoming boundaries in the new space. So, so in particular, cycles can get mapped to boundaries. Okay, so so let's try to see how one goes about doing this. So let's say we have a simplicial map. Let's say F from one complex K to another simplicial complex L. Okay. So you know that this is basically a linear map, right? So it's defined, or it can be defined at the level of simplices. Okay. So F takes each simplex of K sort of linearly into a simplex of L. So this simplicial map is a piecewise linear map in a precise sense. Okay, so you know that if you have mapped some sort of, you know, the simplices to simplices, and the simplices are the generators of the chain group, you might expect that you can extend these maps, again by linearity, to the chain group. Okay, so so this induces a map from the chains of K to chains of the same dimension. Of L. Okay, so to be precise, what we mean by this is that if C is some linear combination of AI sigma I, right, is a P chain of K, then there is this induced map F sharp okay, of C, which is the sum of alpha I tau I, where tau is obviously just f applied to sigma I. Okay, well, I guess I should say that this is equals to f of sigma I, right? If this image has dimension p, sorry, if this it actually is still a p simplex, and then sort of 0 if alpha sigma I, right, has dimension less than p. Okay, all right. All right, so so there's a slight caveat, right, that we only sort of, you know, it's like think of this in the case where you're mapping p simplices to p simplices, and if it ends up being mapped to a low-dimensional simplex, you sort of just discard it. Okay, so this is what we call the F-sharp map. It's an induced map at the level of the chain group. Okay. So you can distinguish now between the boundary operators. It's like on the two complexes, right? So we distinguish the boundary operators on K and L, right, by writing them as boundary K and boundary L, if you will. Okay, all right. So let's see what's happening, right? So you know that the boundary map, right, maps you know, CP plus 1, right, to, well, let's just put it as CP if you were, boundary PK, right, to CP minus 1 on K. And the same thing is true, it's like for the L, it's like simplicial complex. Okay. And then you also have these induced maps, it's like which are for every dimension, it's like of the chain group. So let's say F sharp. Okay. All right. So so one can see, or one can check that you know, with this definition of the induced map on the chain group, right there, it turns out that this diagram actually commutes, right? So it doesn't matter whether you take the boundary of K and then it's like F sharp versus F sharp and then the boundary on L, you end up getting the same thing here. Okay. So the observation is that this diagram commutes. Which is to say that if you have F sharp composed with boundary K, that is equal to boundary L composed with F sharp. Okay. And of course, it's like there is a slight abuse of notation because I'm defining F sharp sort of for each of the corresponding sort of chain groups of different dimensions, right? All right. So you can check that this sort of makes sense, even though we're setting some of the things to 0, all right? If the dimension doesn't match up. Okay. So I'm not going to go too much into details here. But suffice to say that, again, this diagram does commute. Okay, so why is that important, right? So the fact that the induced map F sharp, right, commutes to the boundary implies the following. Implies that it maps cycles to cycles, and boundaries to boundaries. Okay, so how do you see that? Right, so, and in particular, if you take F sharp of the cycle group, Zp of k, this is going to be contained in the cycle group on L. Well, actually, it should just be that, right? Okay. And it maps boundaries to boundaries. So F sharp applied to BPK is contained in BPL. Okay, so this defines a map at the level of the quotients. And of course, the quotients of the cycles by the boundaries are exactly the homology group. So, all right. So I'm going to say that's F star, right? So this is the induced map, which maps the homology group of the complex K. It's like to the homology group, the corresponding homology group, the same dimension on L. Okay. So there's sort of one further observation one can get from this, which is that, so let me sort of just make another remark, right? So the rank, okay, of this, of F star HP of K, right, is less than equal to the minimum of, okay, so I guess this, yeah, right, is of the two Betty numbers basically. Okay, so beta P of K and beta P of L. Okay, and sort of maybe perhaps the easiest way to see this, right, is that on the one hand, the image of this is going to be contained in HPL, so the image cannot have a rank which is larger than the rank of HPL on its own. And then the other thing is that if you take the image, it's like of something with a particular rank, right, then that image has a rank which is again bounded by the rank of the source space, right? So that's sort of easy to convince yourself that the rank of this image, it's like of the sort of the induced map, it's like a level of homology, it's like of the original homology group, HPK, right, has to be bounded from above, it's like by the minimum of these two Betty numbers. Okay, so yeah, so that's this discussion about induced maps, and then we'll stop here for a minute.